Let's take a look at area between curves, but we're going to set up an integral with respect to y. Let's take a look at this diagram to see when it makes sense to do that. If I have a function x equals f of y, so we have a function of y, and another function x equals g of y, and I'm interested in the area between those two curves on a y interval from c to d, well, here there's a clear right function and a clear left function instead of a top and a bottom function. So it makes more sense to use an integral with respect to y in this case. So I have f and g are continuous with f of y is greater than or equal to g of y on this interval from c to d. Now, again, f of y being greater than g of y means being on the right-hand side. Bigger x values are further to the right. And so to find the area between the curves, our integral is going to be y equals c to y equals d of f of y minus g of y. Or informally, we're going to want to use right minus left as the integrand to find the area between these two functions of y. In this example, we want to set up the integral needed to find the area bounded by x equals 9 minus 2y squared and x equals 1. These are both given as functions of y, but they aren't graphed. So let's go ahead and graph them. X equals 1 is a vertical line, and x equals 9 minus 2y squared. So this is going to graph a parabola. It's just that since it's a function of y, the parabola is going to open right or left. And the coefficient in front of y squared is negative, so this is going to open to the left towards negative values. All right, well, now let's go ahead and find the x-intercept. If I let y equal 0, well, then all I have left is x equals 9. So the x-intercept is 9. And so I know I'm going to have this opening left parabola that passes through that x-intercept, but what I want to be precise about is the points of intersection. Where does the parabola and the line intersect? So I'm going to set the two functions equal to each other. 9 minus 2y squared equal to 1. And I'll add the 2y squared and subtract the 1 to get 8 equals 2y squared. Divide both sides by 2, I'll get 4 equals y squared. And so I'll get y is equal to plus or minus 2. So I know that at y equals positive 2 and y equals negative 2, that's where my parabola intersects my line. So let's plot those 2 points. And so that's enough to give us a nice sketch of what this sideways parabola graph is going to look like. So here we have our sketch, and we're interested in the area bounded between these two curves. So this is the area that we're in search of. And we have a clear right and left function. The right side is the parabola, the left is the vertical line. And we can see that the interval is from y equals negative 2 to y equals positive 2. So we can go ahead and set up our integral to find the area as y equals negative 2 to y equals positive 2 of the right function 9 minus 2y squared minus 1 dy. And we can clean that up a little bit. We can do negative 2 to 2, and then 9 minus 1 is 8, so we have 8 minus 2y squared dy. So this is the setup of that integral. We don't have to solve it based on the instructions, but I do want to point out that there is another way to express this area using symmetry. So notice that the area from 0 to 2, so just the top half here, is the same amount of area as the part that's below the x-axis. There's symmetry along the x-axis. So what we could also do, I'm going to put or we could also have the area represented as 2 times the integral from 0 to 2. So instead we're going to go from 0 to 2 of right minus left. And we already know right minus left simplifies to 8 minus 2y squared. So we could make that the integrand right away, 8 minus 2y squared dy. Now, because it was set up, it really doesn't matter which one we choose, but if we had to move forward and actually evaluate this, it would be easier to evaluate the definite integral with a limit of integration as 0, because if we apply the fundamental theorem of calculus, we'll substitute in these values. So it's nice whenever possible to use symmetry, especially if we have to evaluate. What we want to do on this example is set up the integral or integrals needed to find the area of the region in the first quadrant that is bounded above by the square root of x and below by the x-axis and the line y equals x minus 2. But we're going to integrate with respect to y. Well, let's shade the region. We're talking about the region in the first quadrant. So we're really talking about this region here. And again, bounded above by the square root of x, and then below by the x-axis and by the line y equals x minus 2. If we do this with respect to x, we're going to need two separate integrals because the top and bottom functions switch. But if we do this with respect to y, we can see there is a clear right function, the blue function here, the line, and then a clear left function, which is the square root function. So it's going to become one integral if we do it with respect to y instead of two integrals if we do it with respect to x. Now, the issue is that the functions here are presented as functions of x. Y equals the square root of x and y equals x minus 2. So it is going to take a little bit more effort to rewrite these as functions of y. So if I have y equals the square root of x, if I solve for x, then I'm going to get x equals y squared. So here, the square root function as a function of y is x equals y squared. And obviously it keeps going, but we're not going to have to worry about that portion. And then if I have y equals x minus 2, solving for x, I would add the 2 to the other side. So my line as a function of y is x equals y plus 2. So now I have my right function and my left function, but I need my interval to be from the y-axis. So here, the square root function, or x equals y squared, does pass through 0, 0. And then we know that the square root function, if I plug in 4 into the square root of x, I get out 2. So we can see that this point of intersection here occurs at a y value of 2. So our interval is from 0 to 2. So the setup of our integral is going to be from y equals 0 to y equals 2 of the right function as a function of y, so y plus 2, and then minus the left function as a function of y, which would be y squared, dy. So the benefit is that we only needed one integral, but in this particular example, our functions were presented as functions of x, and we needed to rewrite them as functions of y and make sure that we had y values as our limits of integration. In this example, I want to sketch the region bounded by y equals ln x, y equals 1, y equals 2, and x equals 10. Then set up the integral or integrals needed to find the area of the region. We're going to do this with respect to x and with respect to y. Let's start by graphing all of our functions. We'll start with the lines. Y equals 1 and y equals 2 are horizontal lines, and x equals 10 is a vertical line. And now we want to graph y equals natural log x. So we should know the general shape of natural log x is an increasing function, and there's a vertical asymptote along the y-axis. And the other key point that we should know is that because natural log of 1 is 0, this passes through 1, 0. We want to be a little bit more precise about where natural log x intersects the horizontal lines here. So let's go ahead and think about cleverly substituting values into natural log x. So we don't want to plug in something like 2 because we would generally need a calculator to approximate that. What we're going to do is substitute in e. So we know that natural log of e is actually just 1 because natural log and e are inverses, they cancel, so we'll just get out 1. And e is about 2.7. So basically right here is about e, and I'll get out 1. And then the next value I'm going to substitute in is e squared, because again, natural log and e cancel, and I'll just end up with 2. So when I substitute in e squared, I'm going to get out 2. Now, what is e squared? What is, 2.7 squared approximately? Well, it's between 7 and 8, right? It's definitely less than 9 because 3 squared is 9 and 2.7 is less than that. So we'll just approximate and put it right about here is e squared, and we'll get out 2. So now I'm going to go ahead and sketch my natural log x function. All right, here it is. And now we want to shade the region that's bounded by all of these equations. So the region that's bounded by all of them is going to be this region here. So we're thinking about it has a boundary of all of those different 4 equations involved. And if we want to integrate with respect to x, we have to think about top minus bottom. And so if we start at this first point of intersection, which we know now is e, the top function is the natural log of x, and the bottom is just the line y equals 1. And that's true for a while. We have, natural log x on top, 1 on the bottom, until e squared. Because at e squared, then the top function becomes 2, and the bottom function stays 1. So we're basically going to need 2 separate integrals split at e squared in order to integrate with respect to x. So we're looking at our area would be x equals e to x equals e squared. So our limits of integration are x values, and then top minus bottom. So we have natural log x minus 1 dx plus, so we're going to keep adding on more area here, the integral from x equals e squared to x equals 10. That was our vertical line over here at 10. And then top minus bottom is 2 minus 1 dx. Now here we are using calculus, we're setting up integrals, but really this shape over here is just a rectangle. So we could have actually found this area by just doing base times height. Now the base is kind of ugly, it's 10 minus e squared, but the height is just 1. So just something to think about, but again, we are setting up the integrals needed. And so we needed 2. We had a different top over the 2 different portions of this area. But if we instead think about right minus left, then we can just set up one integral. So if I think about actually kind of turning my head to the right, and I can see at that point that there's a clear top function and a bottom function. Of course, if we look at it straight on, we have a clear right function and left function. So we can move forward with doing just one integral with respect to y, but then we have to be careful. Everything needs to be in terms of y. Our limits of integration are going to be from 1 to 2. So we'll have area is the integral from y equals 1 to y equals 2. Our right function is this vertical line, 10, minus our left function. Well, this was given as a function of x, so I had y equals natural log x. If I want to make it a function of y, in order to solve for x, I have to exponentiate both sides. So e to the y and then e to the natural log x. And e to the natural log x cancels and just gives me x. So x is equal to e to the y. E to the y is my left function, dy. So just one integral if we set it up with respect to y, but we needed to work for it a little bit, and then 2 integrals if we set it up with respect to x because the top function changes over the region.